Welcome to the next lecture on entanglement theory. I've lost track of which lecture this is. I guess we've been through a lot now, but I think there's only a few left. So this is a lecture series on entanglement theory for SheQuantum, which is an organization dedicated to supporting women in research and learning of quantum information science. Last time, we started getting into the operational approach to entanglement theory and different entanglement measures. We talked about entanglement entropy and entanglement of formation. And so now we're just going to continue with other entanglement measures. And one that we'll talk about now is called logarithmic negativity. Okay. So how do you compute this? What you do is you have a density operator rho, you take the partial transpose on B, and then you compute the one norm, the trace norm, and then you take the log of that. And maybe it's a bit unclear why you would do this, but for a separable state, if you think about this, if you plug in a separable state, and you take the partial transpose, the result is still a state. Okay, and if you compute the one norm of a quantum state, it's equal to 1, and the log of that is 0. So at the least, this entanglement measure will evaluate to 0 for a separable state. And the same is true for a PPT state more generally. And so what happens is that if the partial transpose leads to a negative eigenvalue, taking the trace norm will register that, and you'll get a value greater than 1, and the log of that will be greater than 0. And so it measures kind of like how different you are from being a PPT state. So what are its properties? It's non-negative for every state. We didn't prove that. We kind of just argued for it now. We did argue one direction, that if the state is PPT, then the log negativity is 0. But it turns out the other direction is true also. So it's faithful on PPT states. That's something you can prove. It's a selective llcc monotone. And it's an upper bound on distillable entanglement. So it is an upper bound, but there is actually a better upper bound in terms of Rain's relative entropy. So we'll get to that later. But what this tells you, since the log negativity is an upper bound on distillable entanglement, that PPT states have no distillable entanglement. So what does this say? If you want to use many copies of the state to do lots of teleportations, you're not going to be able to do them well. And you'll essentially have 0 rates at which you could do quantum teleportation using these states. So they're not going to be useful for long-term teleportation. Okay, so we said that there are better entanglement measures, and let's get into those now. There's better entanglement measure upper bounds for distillable entanglement. So to talk about that, we have to consider a concept called quantum relative entropy. And this is useful not only in entanglement theory, but essentially in all of quantum information theory. It comes up in quantum complexity, quantum communication complexity as well. So it's a pretty important and broad topic. So the relative entropy is a different measure of distinguishability from trace distance, and you calculate it. It's defined in terms of this formula. So this part kind of looks like the von Neumann entropy up to a minus sign. But then you subtract this, sometimes it's called cross entropy, trace of rho log sigma. Okay, so this is the standard definition of quantum relative entropy. This quantity itself does have a physical meaning in what's called asymptotic quantum hypothesis testing, but we're not going to get into that. So what are its properties? It obeys data processing. Remember, this was a basic property that we saw for trace distance. It was a basic property we saw for fidelity, and it holds for quantum relative entropy also. So what does it mean? The distinguishability of the states does not increase under the action of a quantum channel. So that's a very important property. Another one is that suppose you have a state and then sigma is a positive semi-definite operator such that its trace is less than or equal to 1, then the quantum relative entropy is non-negative. Okay, so if sigma is a state, then the quantum relative entropy is non-negative. And furthermore, it's faithful in this sense that it's equal to 0 if and only if rho equals sigma. Okay, so we can use the relative entropy to define an entanglement measure called relative entropy of entanglement. And this was an idea that people had over 20 years ago now. So what do? You take the state of interest and you compare it using the relative entropy to a separable state. And then you take the minimum or infimum over all separable states. And then that's the measure. So it's kind of like asking how close is the state to a separable state with respect to the relative entropy measure. What are its properties? It is an llcc monotone. So indeed, it's an entanglement measure. And there's actually a fairly simple proof for that. So if you want, you could pause the video and try to prove that yourself using the definition of an llcc channel and the definition of relative entropy of entanglement. However, there's something stronger. It's a selective llcc monotone. So that follows from the data processing inequality for quantum relative entropy and what's called joint convexity of relative entropy. So maybe I'll pause here again and say, Samik Khatri and I have this book called Principles of Quantum Communication Theory, a Modern Approach. It's available in the archive. And if you're interested in how all these things are proved, we have a whole chapter dedicated to entanglement theory where we go through the proofs of all these things. Okay, it's convex, it's faithful in separable states, and it reduces to the entropy of entanglement for pure states. So that's nice. It's also an upper bound on distillable entanglement. It's an upper bound that's different from log negativity, but it is an upper bound. We've talked about both entanglement of formation and relative entropy of entanglement. There is a relation between them. So the entanglement of formation is always greater than or equal to the relative entropy of entanglement. So that, delineates some relationship between them. And there's a simple proof for that. We can just talk about it here. For the entanglement of formation, you have to consider pure state decompositions of the bipartite state of interest. So let's suppose we have one. Then we can take the average entanglement entropy of the ensemble and use the fact that the entropy of entanglement is equal to the relative entropy of entanglement for pure states. That's something we're just going to assume. And then use the fact that relative entropy of entanglement is convex. So then you can bring the sum inside. This inequality holds for all possible pure state decompositions. So then it implies this inequality at the top. So that's an interesting little mathematical proof if you're into that. Okay, so now what we're going to do is we're going to combine the concepts of log negativity and relative entropy of entanglement into a single concept or entanglement measure. And that's what Eric Rains did roughly 20 years ago after that other work on relative entropy of entanglement came out. And instead of optimizing over the set of separable states, he said, let's define a new set where we include all positive semi-definite operators such that their log negativity is less than or equal to 0. So that will include the PPT states where this is saturated, but it's also going to include more positive semi-definite operators that are not necessarily states. So that was the idea that he had. It was very brilliant. And this entanglement measure gets used a lot. Okay, so it is an llcc monotone. That follows because the set of separable states is contained in the set of PPT states, and PPT is contained in PPT prime. So then you can use that fact to conclude the llcc monotonicity. As far as I'm aware, it's an open question to prove that it's a strong llcc monotone. I don't know if anyone's proven that. It does not appear to be simple. It does reduce to the entropy of entanglement for pure states. The main application of the Rain's relative entropy is that it's a tighter upper bound on distillable entanglement. It's tighter than relative entropy of entanglement, and it's tighter than log negativity. So if you're trying to bound distillable entanglement, it's better to use the Rain's relative entropy because it'll be tighter in cases of interest, in some cases of interest. Additionally, a nice feature is that you can calculate the Rain's relative entropy. Okay, so I've been talking throughout these lectures about MATLAB and how you can use CVX. You can also use QETLAB, QETLAB. So if you download some other packages in addition to CVX, they're all free. You download CVX Quad and the quantum information package by someone named Toby Cubitt. So you download those, and then you can write this program. And what it's doing is computing the Rain's relative entropy for a randomly chosen 2-qubit density matrix. Okay, so this is a convex optimization problem. You're optimizing overall operators in this set. I'm calling them tau in the program. And then you're just minimizing the quantum relative entropy function between the state of interest rho and tau. And then the constraints are tau has to be positive semi-definite, and the trace norm of the partial transpose operator has to be less than 1. Trace norm is also called nuclear norm. Okay, and then the output will be the Rain's relative entropy. So it's a pretty simple program that you can execute, and its running time will be polynomial in the dimension of the state. So that's nice. Okay, why don't we stop here, and we'll pick up next time with squash entanglement.